Welcome, everyone. I guess for myself, one of the highlights today. So I have now the real honor to introduce to you our next speaker, Daria Soboleva. Let me say a few things. So Daria is the head research scientist at Cerebras and has traveled all the way from Silicon Valley just to be here today with TNG for our big tech day. And so we're excited and thrilled to have her I want to give you 3 reasons why we are so thrilled to have her. First, Daria creates groundbreaking work. So for example, she has created Slim Pajama, a 627 billion token dataset, which has become one of the industry standards. Second, her current research and her talk today focuses on mixture of experts, which of course aligns with the research that we do with our camera models. So great to have her. And third, and I must say maybe the most important reason for today, is that she is a great educator. She has published over the last month a really great series of blog posts explaining the mixture of expert architecture, both in a very detailed but also very understandable way. So we thought it is really a perfect fit for our big tech day, perfect speaker. We're glad to have her. So for her talk, Sparse Models are the future, a deep dive into mixture of experts. Please join me in giving a very, very warm welcome to our next speaker, Daria Soboleva.
Thank you. Thank you, Fabian. Hi, everyone. My name is Daria, and I'm super excited to be here today. Thank you for having me. My talk today is going to be about sparse models, and I'm here to convince you guys that they are here to stay, and they are the future. And specifically, we're going to deep dive into the mixture of experts architecture. Some of you may have heard about this architecture before. We also had other talks, like Fabian presented that. I will try to give you a bit more flavor on how these models are trained and what really happens at scale. And the first thing about me, so I'm a head research scientist at Cerebras, and Cerebras is a startup company in Silicon Valley, and it basically makes hardware chips, so it's a hardware company, and you might have heard that we are the fastest inference on Earth. I'm going to cover the hardware part of Cerebras side as well, because we train mixture of experts on it. This is my official title. My unofficial title is MOE Queen, and it's been given by my colleagues and friends. And mostly because for the last few years, I have been focused on mixture of experts architecture, and in general, my research focus as hardware-efficient LLM training. I guess some previous works that I did, so Fabian already mentioned I worked on Slim Pajama dataset that at the time when it was released was the biggest, cleanest, deduplicated dataset that was used by a lot of other LLMs. And it became state of the art, received a lot of downloads. And prior to my work at Cerebras, where I've been for almost 5 years by now, I worked at Google. And also trained models, NLP, and speech. For the agenda for today, I kind of want to start with some introduction what LLMs are, and then we're going to switch focus to the mixture of experts. But I also want to give you like an idea of trends that happened in the field. So when we started with dense models, and now we are using sparse models heavily. And then we're going to talk about MOE at scale. So how do you scale them, whether you use GPUs or whether you use Cerebras hardware? What are the issues, how you solve them? And the last part is the most interesting part for me. I'll ask you guys to ask me questions, or you can ask questions after the talk. Actually, that's all about me and the agenda, and I want to know you guys a bit more. So how many of you heard about LLMs? Raise your hand. Oh, that's a lot of hands. That's exciting. So we're going to be like really brief here. LLMs are based on the transformer architecture, which was developed almost a decade ago. There are different types of layers, and we're going to go into details of what our different layers are doing, and specifically why a mixture of experts does what it does. So now, LLM evolution. A few years ago, we started with dense models, and the largest model that was released at that time was the GPT-3 model released by OpenAI. That model had 175 billion parameters. It was dense. And basically, in addition to the model release, the OpenAI released the paper that showed the scaling law projections, which showed to us that we can continue increasing the model size and make it more intelligent, right? After that, there was an era where we said, in addition to scaling the model size, you also want to scale your data. So if you guys heard about Chinchilla paper and the scaling law that projects what would be the best ratio of tokens per parameter, this is how the Llama 3 was released. The product of that research was the family of Llama 3 models. So they're not just larger in size, but the 400 billion is larger anyway, but they also were trained on more data. And that was the era where I worked on Slim Pajama and a lot of other cool people created data sets, deduplicated data sets. We spent a lot of time on juicing out the most out of our dense models. But to continue scaling further, we realized that we actually need to change the architecture as well. And this was, I think, December 2024, when DeepSeek AI team released their DeepSeek V3 model. This model already has a mixture of experts architecture, so it's no longer dense. And it had about 671 billion total parameters, but it only activated 40 billion for a given token. So it's more efficient to use that and scale that. Now, this slide is about why DeepSeek V3 mattered and why we all care about mixture of experts. So you see here that there are different benchmarks and different open source and closed source models benchmarked against it. So DeepSeek V3 was beating not just open source models, but closed source, which was one of the key improvements in the open source community. And I think one of the interesting benchmarks here is called GPQA Diamond. That one is designed for PhD level questions that are hard to answer for like a generalist person who is good at everything. And the 65% accuracy is a human level accuracy. You can see how close our DeepSeek V3 model is to that level. So that was one of the innovations, and it comes from the architecture, because this architecture allowed us to unlock the new capabilities of LLM models. Now, before I give you the math of how mixture of expert works, I kind of want you to give an idea what's the problem with the standard dense LLM. On this text, an LLM has to do a lot, right? So it has to understand that TNG is the company, and that Big Tech Day is the actual event. And it takes place on October 24th, the date, and the location. It takes place in Munich, in Germany. So when you have just one model that's a generalist, parsing this text is going to be a hard task. It's not going to be super accurate with whatever other prompts you ask about this context. But we want it to be more accurate. So for that, what we're going to do, we're going to look at the different layers that dense network has, right? Remember, we have embedding, multi-head attention, and feed-forward. And what we're going to do, we're going to analyze what is the role of different layers. So for example, embedding is simple, right? It translates the token ID into the hidden representation. So the LLM can parse it. Multi-head attention tries to find connections between different words in the same sentence. What does feed-forward network do? Any guesses? OK, I'm going to answer that. So we believe, from the interpretability perspective, that feed-forward network is sort of there to disentangle information that comes from the multi-head attention, right? And usually, it is designed as like the two fully connected layers separated by the nonlinearity. So see, like the embedding layer and attention layer are super structured. You give the model an exact task that it has to learn there. But with the feed-forward network, we kind of throw it, at it and hope for the best. So it's not really efficient to have just one set of fully connected layers. Because of that, we create multiple experts. Basically, each expert is just a copy-paste of the same FFN block, or the fully connected layer. And what we're going to do next, we're going to try to train the model in a fashion that specializes each expert on a certain domain or on a certain subspace, right? For that, we're going to augment the architecture and add another network that's called the router. And it's going to be placed right before attention. The router's job is now to decide which particular experts should be selected for a given token. So when you have a full batch of tokens, you're not moving those tokens in the batch to all the experts. You only move them to a portion of experts. You subdivide your batch size. And essentially that allows DeepSeek V3 to have 600 billion parameters in total, because you created a lot of experts, 256 in particular, but you only activate a portion of them, like a very tiny subset. I think it was 8. So that's the whole idea of the mixture of expert models, like from the interpretability perspective. But I also wanted to give you some sort of like explanation from the optimization perspective, right? So when we train our models, we usually use some gradient-based method. So most of the models are using AtomW, but you can do your interpretability analysis on the gradient-based method, like SGD. What we have here plotted, imagine that I plot tokens that arrived just before the feed-forward network. How do they look? They usually look like this Gaussian bulb at the left side, so it's kind of like very rounded distribution, and it kind of meshed together. So it's unclear how FFN should find like specialization in different domains. It has to learn the representation that's good for all of these tokens in the whole bulb. What mixture of experts are doing, they are separating this bulb of tokens into the cones. So on the right, you can see here that we separated a cone of tokens that belong to the blue color. What we want the expert to do, we want it to specialize only on that domain. So it can be really, really bad on all other tokens in the batch, but it has to be good on that. What it does for optimization perspective, it improves the amount of signal you have thrown at the FFN network. And it also reduces the amount of noise. And because of that, mixture of expert works. So it converges to the same loss as the dense network faster, because you now have only, like you created specialized experts that converge faster to a better local minimum. Or if you, for example, flop match to the dense network with experts, like here, for the same number of flops, I'm increasing number of experts and improving the quality, you obtain better loss. Now, this is the theory still, like even though this is an actual experiment that I ran, but the theory comes from the flops, right? Like when we say we want to achieve the same number of flops or we want to train faster, we actually talk about the wall clock time reductions, not the flop reductions. And when we run actual experiment to see how our theoretical flop reductions translate into the throughput, we actually don't see it in practice. So when I run onto multiple GPUs, I see that MOEs are actually slower than dense, so you are not getting to the optimum faster. Any guesses why this could be the case? You already know my slides. OK, let me then explain it. So when we have a large model, we usually use multiple GPUs. And when we use multiple GPUs, we need to spread this model across multiple GPUs. So there should be some model parallelism employed, because GPUs are limited in the amount of memory they have, right? The typical model parallelism for a mixture of experts is called expert parallelism. And there, you basically subdivide experts because they process independent tokens. You can position groups of experts on different GPUs, and everything else, like attention, layer norms, they're just copy-pasted. Those are the same. So when you're talking routes, when your token goes through from the bottom to the top of the transformer, basically when it goes to the router phase, the router decides which expert is best positioned to process this token. And this is where we have to go through the all-to-all operation. That one shuffles tokens between the GPUs so it can find the expert that we selected in the router. Then experts process these tokens, and we have another all-to-all operation that does the mixing of these experts together so we can produce the final output. And that all-to-all operation is the bottleneck. So you're right, communication is the bottleneck. So essentially, if we take, let's say, the state-of-the-art model, Qwen3 model with 128 experts, and profile how much time we spend on the compute versus how much time we spend on communication in the MOE layer, turns out that 77% of the time is spent on communication, and your GPUs stay idle, and you are not getting flop reductions into the wall clock time reductions. Now, how can we fix that? Unfortunately, there is no solution to the architecture that GPU has. They have limitations. Usually we connect like loads of small chips together. You can see that the size of this chip is 800, this is H100 chip, 814 square millimeters. You connect a lot of them, and you have a lot of wires. And those wires have the bandwidth, right? And you cannot physically go beyond that bandwidth. So to resolve the communication bottleneck, you might want to consider a different type of hardware. So I want to compare H100 GPU, the design of it, with the Cerebras WSE. So one important thing to highlight is that GPU doesn't really have SRAM memory to train large language models. So SRAM is 50 megabytes. There is a different memory that's called HBM memory that has the actual 80 gigabytes of memory for H100. And you have to store most of your weights there. So you cannot, in activations as well, because you only have 50 megabytes close to compute units. And your memory bandwidth is quite limited as well. It's 3 terabytes per second. So you cannot move data, the weights faster to the chip. With Cerebra's chip, the picture is different. So the size of the chip is much, much larger. And you can imagine the size of a dinner plate. That's the chip size. Though usually it's American dinner plate, so it's bigger than the European. Anyway, so here we have a larger chip, and it has way more SRAM memory. So it's 800x more SRAM. And memory bandwidth on that chip is also much, much higher. So you have like 7,000x more memory on chip. Because of that, we can actually store models on the chip directly without having the need to move between HBM and the chip itself. And the 44 gigabytes allows us to go with 1 billion size models on the chip without any parallelization techniques. But you might ask, why do I care about 1 billion if Kimi K2 is 1 trillion? So there is a technique to allow us to train 1 trillion models on the chip directly without any model parallelization as well. It's called weight streaming. Weight streaming is a technique that allowed us to sort of disaggregate compute and memory requirements on the chip by connecting additional memory nodes directly to the chip. So the memory bandwidth that I showed to you on the chip is the same as when we connect these additional CPU units. And these CPU units store all of the model weights, so we never realize the model weights on the chip itself. And we stream the gradients and the weights back and forth between the chip that does the calculations and the memory X nodes. Because of that, you can literally go to, and that has been tested, 1 trillion model size on the chip and beyond. There is no limitation like that. It's not practical to train the 1 trillion model on just one chip, but you can do that because of the architectural differences with the H100. And because of that, we never have a communication problem that GPU has between the experts, because experts are positioned on the same chip, so they are very close to each other. And the memory bandwidth on the chip, you saw it's in petabytes. Cool. Now, when you run stuff at scale, even on efficient architecture, you need to profile, you need to do a lot of engineering tricks as well. So the first time when we launched an MOE model on the Cerebras hardware, it was also slower than the dense network. Why? So if you guys, again, profile an MOE model, you will realize that we subdivide the batch size in MOE layer, and we do that for the reason that I described. We want to extract higher signal and less noise, but as you increase the number of experts, you subdivide more and more. And at some point, but you allocate a lot of memory, you still have all of your experts allocated. At some point, the batch becomes so tiny that most of your time is not in compute. Most of your time is actually memory movement or allocation of the bytes, etc. So it's not really efficient to continue like that. We need to change the arithmetic intensity in the MOE layer. I guess the number here, which is 98%, also comes from my analysis on Qwen 3. When you go to the extreme levels of sparsity, and I will show you the plot, then you can most of your time can be actually spent on other layers. And the MOE layer is really, really fast, but it's not efficient because you are not utilizing hardware that you allocated. And sorry if I didn't mention, but arithmetic intensity is the flops you spent, how much compute you spent, versus how much memory you spent, so that's fraction. Now, at Cerebras, to solve this problem, we developed a new technique which is called batch tiling on attention. Essentially what it does is we know that we subdivide the batch size in MOE layers, so it becomes really tiny at some point. Can we increase the batch size without changing the MOE architecture? And the answer is yes, you can. So what we do, we look at the previous layer, which is attention, and that one processes the full batch. So what we can do, we can tile that full batch into the G sequences, combine the results together, and increase the batch size for each expert by G. So this parameter becomes a hyperparameter. You can find the best one depending on the sparsity level. That allows us to restore the arithmetic intensity for MOE layer compared to the dense network. And here is some empirical analysis on a Qwen3 model. So you can see the dense model baseline and the baseline with MOE model. You can see that as we increase the sparsity of increasing the number of experts, or for the same number of experts, you decrease the top K, that also increases the sparsity on the network, you become slower. And at some point, that's not really efficient to train an MOE model. You can publish a paper, you can say it saves you flops, but it's not really improving the throughput. So it's not practical to train it. What we do with the BTA, when you configure that G, depending on your sparsity level, you can restore the throughput of the dense network for the same number of flops. And that allows you to do what I said in the beginning from the theory. I want to train an MOE model for the same number of flops. I want to receive a better loss. You can do it now. Or I want to train an MOE model faster to the same loss as the dense network. You can also do it now. Key takeaways. So MOE models is the current state of the art, and it's here to stay. It's the only practical way to go to trillion parameter sizes and beyond that. There are some talks about other new architectures that we haven't realized yet at scale, so MOEs is still a go-to architecture for training models in scale. However, architectures like GPUs have limitations that unfortunately you cannot work out in the software side. You have to work out it on the hardware side. And on Cerebrus, we designed the architecture that specifically designed for LLMs with in mind that the sparsity, we designed it like 10 years ago, with in mind that sparsity would be the key feature, which it is right now. But there still, you have to profile where your flops are spent, where is the memory leakage, etc. So there are ways to work around it, but you still have to keep it in mind. And one other thing I wanted to mention is that I think open research is a really important thing in the community because it moves the innovations forward. So DeepSeek v3 was created inspired by that. And you see that there are a lot of adoptions of this model and a lot of innovations on top of it, which is pretty exciting. And I'm super proud that Cerebrus, as the company, supports open research. So one thing that we recently did, we created a series of MOE blog posts as a part of the 101 guide. There, we discuss practical issues of MOE models from different parts of it. So there are 5 different blog posts that we released that cover everything from why mixture of experts is an architecture to go with, to how to train it efficiently and how to serve these models efficiently. So the last blog might be mostly interesting for people who are serving the MOE models. This is the QR code to the blog, if you want to read that. We finalized the MOE guide, so it's essentially over. The last episode was released on Monday, right before my trip. But we still have loads of content that we didn't put out yet. If you guys are, if anyone just texts me and asks me some questions, I'm happy to see if we can continue this series. And yeah, if you have any questions to me, if you want to talk about what's next, what next for MOE models, what we are doing at Cerebrus, or in general want to know more about LLMs and efficient training, stop by or DM me on X. Thank you.
Right. First of all, thank you. Right. We have room for questions. Oh, come on to the back. I see you so far.
Hi, thanks for your talk. How much does your chip cost and where can I buy it?
That's a great question. I think we should chat offline, like after the talk. You can definitely rent the chip. I think we have it on our website for the inference side, but if you want to train it, then you have to talk to me.
Oh, that's nice. Perfect.
I had a few questions. The first one would be, so you were talking about the routing layer and how it routes tokens to like particular set of experts depending on the domain and so on and so forth. But like a token can mean different things in different contexts, and just one, if I think of it as words, then a word, I mean, there can be significant overlap between the expertise of different expert models. So how does the routing model kind of route in that situation?
Okay, so there are different types of routing. Oh, was there more?
Yeah, but maybe it'll take a bit of time to answer that.
Okay, I'll try. So there are different types of routers you can have. The most go-to architecture right now is like the learned routing method with softmax nonlinearity on top, kind of like switch transformer paper inspired. But there are other routers, like there's hash routing. You can just have a hash function implemented that routes tokens to different experts. There is also like Syncorn, which is a bit more advanced. So you can control the router depending how you want it. If you want to route, if you want hard-coded routing, you can implement it that way. Now, maybe the question is like, how does learned routing decide which expert to select if all experts are similar, right? So actually, that's a very good question. As of today, we don't actually have any good way to kind of like force specialization in experts. So we sort of hope it will emerge at some point if we don't like control for load balancing pretty heavily. And it does happen. So if you train an MOE model and like look at the load balancing loss and specialization, whatever way you measure it, you will see that in the beginning, MOE model just balances between very similar experts. But towards the end of training, it actually tries to specialize. So it will be less balanced. Some experts will not be selected as often. There will be kind of like an emergent experts that are popular, and this is one of the reasons why DeepSeek v3 had shared experts, because they are always selected, right? But this is an open question, open research question. How do we make experts more specialized? Because it actually hurts a lot when you try to deploy the model, right? So we train this model as like ML researchers. It's great, it's big, it's nice. We don't care how people are going to use it, but when people start using it, it becomes too costly because you have to load all of the experts into the GPU or GPUs, right? And you are not using these experts, right? Because you either like load balanced other parts of experts or, yeah. So it's an open research question of how to differentiate experts, and it's not yet resolved.
Thanks a lot. And one more question would be, so you were comparing Cerebrus WSC with like the H100 chip and so on, and you were saying, yeah, when we have like, with a multi-GPU setup, you could be comparing one Cerebrus chip. What are the trade-offs, or like, what is the catch?
What is the catch? I guess like, I would say this way. So Cerebrus as a company has been out there for a long time, and we have been training this transformer architecture since like 2016. Because of that, even though it's a unique architecture that has its custom kernels, so we don't use CUDA kernels. It has evolved a lot, like because we work with customers, we train these models. But originally, you have to implement like all of these ops that GPU support on this new architecture. So it takes time to be like generalized platform, right? So even if right now, like we are heavily specialized on transformers, but if you go like to a very like specialized hybrid architecture, that might not be as efficient as if you run it on the GPU. But yeah, it just has to be like tuned a bit to that. But maybe I didn't mention like why Cerebrus is great, like apart from just being bigger, right? When you because when you have some type of model parallelization on the GPUs, when you set multiple GPUs together, if you try to like measure the throughput, it's not linear as you add more boxes, right? The reason is because you have this communication bottleneck and the bandwidth limited wires really prevent you from that. With Cerebrus, when you stack multiple chips together, because you don't have any parallelization except for data parallelization, you have a linear improvements in the throughput, which is like the key point.
Yes. I also have a question. So I heard with this wafer scale engine, you have 100% yield in the fabrication side, which is very impressive. But does that mean, so you have to turn off certain tiles because you have arrays of these? So does that mean that not every chip has exactly 44 gigabytes SRAM? So you have to take that into account when you're training by having some buffer?
Right. Yeah. So it's slightly. You can think about like 40 gigabytes of on-chip SRAM for CS3, but we are releasing the next generation, so there will be different trade-offs as well. But yeah, you're right. There is a buffer.
Thank you so much for the nice talk. What's about different architectures? Do you get like a similar performance boost over GPUs when you're like doing some diffusion models or like some other data analysis tasks like other than mixture of experts?
Yeah, this is a great question. So I would say before we would heavily optimize dense networks, so those are really, really fast on our hardware as well. And we sort of go with, I guess, like what's open source and what's popular in the open source community, as well as what our customers want. So we work with multi-model models as well. So like Lava-based architectures. And yeah, like we explore these domains. I guess like diffusion is something that we are trying right now and trying to see if there is benefit in running these architectures on our hardware versus GPUs. But I don't think we published anything on that yet.
Thanks for the nice talk. Could you compare your concept of the mixture of experts to one LLM querying specialized LLMs for an answer?
Let me rephrase the question. So is the specialized LLM better in that specialized area compared to having a mixture of expert model that has an expert that specializes in it? Okay, this is a great question. And I think there has been some research on that area as well, where we take a set of specialized models and we try to combine them together and train them like in a unified fashion together, so you have one model at the end still. That seems to be still less compute efficient compared to the mixture of experts architecture. So yeah, customizations like that are hurting the generalization of the MOE model.
Thanks for the talk. Are the types of experts in some way predefined, or is it all learned on the way?
Type of experts. Like if you can ask the model to specialize experts in one particular domain in advance, that's the question. Yes. You can, and the router's job is actually to do what you want, right? So if, for example, I have the data set that consists of different types of domains, they can be like Wikipedia, Common Crawl, I can pre-process the data set, so I store the token ID and the label where the token is coming from, and I can create a router that just routes based on this label, right? This way, one expert will be trained on Wikipedia, another on Common Crawl, etc. That work has been studied, and it's less compute efficient, that allowing the model to kind of emerge how it wants to specialize. And maybe to answer this question a bit more detailed, we study a lot what this specialization actually means, and if I try to answer the question what specialization is, it's probably going to be different from what Fabian would say, let's say, and other people who study mixture of experts. So I do believe that domains is a bit too high level for MOE. You want something like different transformations. So if I route my token through expert number 1 and I get some output, I want the output to be different from if I route the same token to expert number 2. And that comes to like linear algebra and like SVD and comparing the SVDs. Yeah, we don't have any models that I'm aware of that have very good specialization, if it defined the way.
Thank you very much for the talk. This is also a question that there has been a lot of research on, but what I'm finding hard is to have a proper intuition. It's the number of selected experts, the top K. There are some ablation studies from DeepSeek which came to the conclusion that 8 actually is a good number. Now there's K2, which also has 8, but they have a different number of experts in the layer. And I wonder, is there any kind of intuition which would say, well, why don't we go to 10 bits to route instead of 8? Or why don't we go for 16 and try it out and come up with a completely more fine granular structure? Is there something like an obvious next step, maybe just because somebody hasn't done it yet or capability of GPUs increased, that one would like to look at? Or did the titans on whose shoulders we are standing already found the right solution with using top K equals 8?
That's a good question. So I work a lot with other researchers and collaborate with them, and they all have this kind of their own thoughts on what should be the optimal number of top K. So I guess like the high-level problem is this research recently hasn't been super open. So when DeepSeek v3 publishes their numbers, they say we use top K8. And then now if you look at kind of like the Hugging Face community, it all uses top K8, right? Why? It's unclear. But the main issue comes from there is a lack of good methodology set that when, let's say, when OpenAI released the GPT-3, they released the scaling law. And that's the methodology, right? You can follow the scaling law. Everything else is kind of unclear how you study that. Because do you select the top K prior to batch size, prior to learning rate, prior to filter sizes in experts? What's the order in those? What scale you can go with? And also, like, I don't know if you guys ever know, but there is this MUP community, maximal update parameterization, that kind of helps you transfer the optimal hyperparameters from small models into large models, but not everyone actually adopts that. So DeepSeek v3 didn't use that, so they had to build a scaling law for learning rates, etc. Now, I guess like this is too long of an answer, but top K8 is not optimal for every expert count. For how we do it, like we find the compute efficient expert count, and sorry, we find the compute efficient top K for a given expert count together with the filter size for each expert. So if you increase the top K, you might want to reduce the filter size. So you activate more, but you make each expert smaller. And it all usually is studied against the scaling law. But you have to have the methodology so you can actually experiment with that and get some insights. Yeah.
Hi, thanks. So I'm not an expert in the field by any means, but the impression that I get from what you're saying is instead of taking an expert and training it, you essentially define your routing and then hope that your experts become experts in particular fields. Is that correct?
So it depends on the router. If you can do it that way. But the way that we train models and the way that's more compute efficient is when you have a router as just a linear layer with some nonlinearity on top, like a softmax or a sigmoid. And you want the router to learn how to route tokens to different experts without other constraints other than like load balancing laws, right? We want to load balance between different experts, and that's the only constraint you have. Experts themselves usually are copy-pasted, so you have identical experts with some caveats, like you can have shared experts. Some people try it with different sizes, but I haven't seen much compute efficiency gains from that. You initialize them randomly, but the same structured initialization. Because they're initialized randomly, once you train the model, they will learn different things. So that's how we usually do it in like state-of-the-art MOEs.
So I have a follow-up question to that, which is talking about DeepSeek and the idea that, they tried to essentially build some sort of censorship into some of the experts. So how does that fit together?
What do you mean by censorship?
So that there were certain experts that were responsible for ensuring that the responses that come out were aligned with the ideas that the designers wanted.
Okay, that's a very. I think DeepSeek v3 was
this
really hyped.
This might be a too loaded question for you to answer. Sorry.
No, actually, so if we study the DeepSeek v3 routing, there is no that much novelty, and there is definitely not that much work in ensuring specialization. DeepSeek v3 really tried to ensure load balancing is good because they have a huge model they have to parallelize across GPUs, and they want GPUs to be utilized when you employ expert parallelization. So in addition to load balancing laws that we have in switch routing, like a learned routing, they also have this expert bias streak, but it just does a more, I guess, like accurate job in load balancing. Because when you have a loss that regularizes for load balancing, it's really far away from the router. And when you do the backprop, the gradient signal is getting is very small. So expert bias adjusts the logits that comes from the router. So then you kind of like force harder load balancing in the router itself, in a particular layer itself. So yeah, load balancing also it's not per layer, it's usually averaged across layers. It's harder to maintain balanced workloads per layer. But there is no specialization that DeepSeek worked on.
Okay, I think we take 2 more questions and then we release you.
Hey, so thank you for the great presentation. And my question is, I was curious the whole time, like, is there some neurobiological analogy with this routing and expert concept, like some kind of routing in the brain or anything like that?
Yeah, well, exactly. So when I talk to people who study brain, some of them tell me that our brain is activated at 100 capacity at every given second. And some other people tell me that we don't actually activate the 100 capacity of it, like we have much smaller percentage. I think I'm more aligned with the second crew, because I think if my brain worked 100% every second, maybe that would be bad. But yeah, so because of this second analogy where you activate only a portion of your brain for a given information, then yeah, you can have the same analogy with mixture of experts. But I think brain activates it in a dynamic fashion, mixture of experts activate it in a structured fashion. The dynamic routing, the dynamic sparsity is still yet to be realized with these architectures.
Thanks for the great talk, very close to the hard metal. One thing, is there, you have given some arguments that speak in favor for a mixture of expert models as compared to dense models. One thing that comes to my mind is interpretability. It seems to me, I'm not an expert here, but that there's a lot in favor of mixture of expert architectures when it comes to interpretability somehow. You have a better kind of access maybe in this layer to interpret things. And interpretability is a big pressure on all LLMs. Is there something that speaks in favor of mixture of expert also when you see we have to find answers to interpretability?
Yeah, so this is a great question. I love interpretability of LLMs as a field, and I think that has to be more studied. So when I was describing in the beginning what's different roles of different layers, and the whole idea why we like split FFN in particular, not attention, is because FFN has this job of sort of like, which neuron should I activate when I see like a Golden Gate breach in a text, right? So from that perspective, you want to make the job for that layer easier because it's the hardest. Everything else kind of already knows what it has to learn. And in that way, right, like when you split FFNs into multiple experts, you make each expert's job easier. It doesn't have to learn everything. It just has to specialize in one particular domain. And well, it has to activate one set of the neurons out of like all of them. It's only responsible for those compared to the generalist FFN. Yeah.
Okay, so I think if we would take a number of good questions as a measure for quality of a talk, then we have really a winner here today. So let's thank Daria again for this very great talk and all the questions answered. Thank you so much for joining us. And enjoy the rest of Big Tech Day. Thank you.
Thank you.